Okay, let us look at another differential equation. So the differential equation that we'll try to go through today is the first order linear ordinary differential equation, which we normally will solve using the integrating factor method. So the standard form of this equation is simply as follows. So it's a plus, so it's a p of x here, y is equal to q of x. So if you're solving some differential equation problems there, and the standard form, you find out that the standard form is of this kind, then the steps that simply you just have to follow after we have the standard form. So simply just have to get the integrating factor, which is equal to e, then the exponent, the x. So after we have the integrating factor, simply just have to apply it into the formula here. You multiply y with the integrating factor, so equal to, then perform some integral, where the integrand here is actually a product of if and a q of x times the dx plus c. So y appears exactly once, as we actually see in this formula here. So we can easily make y subject of the equation. So y is equal to 1 over if, can open brackets, and then we simply just have if here. So q of x dx plus c. Right. So this really is all that you need to do. So simply just have to find the standard form, is very important. After that, so just have to find the integrating factor. Then we simply just have to go through this formula. Then make y subject of the equation. Then we have the solution. So the next thing that we really just have to do now is simply just to have some examples, try to apply this technique. But what I thought maybe it may be nice to do, because we are applying only just formulas here, I thought maybe it will be nice to see where these formulas come from. So let me try to show you where the formulas come from. Trying to mark the end of the screen here. Okay, so the differential equation that you have, in fact, maybe if I take you back from what we had yesterday. Remember the separation of variables? So this equation, it starts with the same form of a differential equation. They look the same, but what makes them differ or makes us to solve this using different methods is actually the right hand side, this f of xy. So for the first order differential equation, which we solved yesterday using separation of variables, we want u of x v y. So it means our f of xy must be able to be written as a product of a u of x and a vy like this, which you can then further separate with equality sign and integrate left and right hand side. So in this situation here, what we have today, so we are having dy over dx, if we may write the f of xy as a u of xy plus, let me use q of x. I'm borrowing q of x from the standards form there. So a couple of things can happen here. The first of those cases could be, for instance, if q of x is equal to 0, what you see is that this differential equation, it goes back to that form of separation of variables, which therefore we can solve using separation of variable method. The second thing that can happen also is that q of x is equal to u of x. If this is the case, it therefore means we have a dy over dx is equal to u of x. Remember, u of x is now equal to q of x, so I can just one of the two. Then it leave us with a y plus 1, which also it simply takes the form that we normally will solve using separation of variables. Okay, so another thing that can happen also is that the q of x is not equal to u of x. So if this is the case, then you are not able to apply our separation of variables here. Then we have to find some other way to solve this. So the people who solved this problem before us, so they were creative enough. They saw that, you know what, if we are facing a differential equation of dy dx is equal to f of x, this differential equation we can easily solve with just integration, because what you can do is to integrate the left hand side, integrate the right hand side with respect to x here. Then you simply just plus a c and you'll get a solution from here, right? And this equation that we are facing here, it can be manipulated into this form, right? Okay, so let us then start the manipulation. So what we say here is that the right hand side do not have any y variable. So let us therefore try to do that. Remove y variables on the right hand side. So instead of saying minus u here, I'll say plus p of x, because again I want to go to the standard form that we wrote. So one can say, maybe say p of x is equal to minus u of x, is fine. We just have a plus p of x y in our standard form, so I want to go there. So this is equal to q of x. So we have achieved something on the right hand side, q of x. There is no y variable. We are happy. Now the issue is on the left hand side. So the left hand side have two terms. On what we have here, we're only having one term. So we must find a way of taking all of these two terms into a single term, and that will be wonderful. So in these two terms, what we say is that we are having a y, and we have also its derivative. So this is actually very special. So one thing that you can do that we hope it will help, we don't know, we hope it will help, is how about we multiply left hand side with some unknown function if, multiply all the terms on the left hand side with this unknown function, which we hope it can actually give us some assistance here. Is equal to, of us, what to do on the left we must do on the right. Therefore, so goes the right hand side will also be multiplied by this unknown function, right? So what is the target? Why are we doing this multiplication? Our goal here is to put together these two terms into a single term, because what we want to actually get something of this kind, right? So in these two terms, we say that y, as we have already mentioned, there is its derivative. So we can actually get one term if this can also have its derivative sitting there. What is the meaning of that? The meaning of this is that we have a product. So remember the product rule. So it's simply just you have a derivative of a product of two functions. And what are those functions? Is this unknown function if. We are hoping it must give us or it will be able to give us the product here multiplied by y is equal to I f times q of x on the right hand side. So therefore, if we apply this differentiation, so we will get d over dx integrating factor times y as per the product rule. Therefore, integrating factor times d over dx y is equal to if times q of x. This is the target, if possible. Now, the reality, of course, is sitting here. Then, this is what we hope this if function can help us achieve. So if we can compare the two, you can see that on the right hand side, we are happy. The right hand side of what is here is equal with what we have at the bottom there. What about the two terms on the left hand side? This term here, we also are happy with it. Our only problem here, it only is this term and this term. So therefore, for these two equations to be the same, so it means we must deal with these two terms. We must try to have a way to equate them. They must be equal. So of the two terms here, they both have y and a y, so that one is not of concern. But what of concern here is that the if times a p of x, it must be equal into this derivative of this unknown function if. Right? Let me write it nice. It must be equal to the derivative of some unknown if function. Right. So from here, what we see is that the p of x is equal to the derivative of this stranger here, if divided by if. Right? That's what we see. If we can integrate both left and right hand side with respect to x, we will get a p of x dx is equal to the derivative with respect to x, if here, all over if d of x. This will therefore give us a ln if on the right hand side, which we can happily solve with the exponentials, and it therefore means if is equal to a raised to p of x dx. Right. So what does it mean? So it basically means that this exponential function is what can help us put the two terms on the left hand side into a single term, therefore going there into this situation of f of x, which you are trying to achieve. Because you can therefore just happily say y is equal to, the integral on the right hand side. The idea is that we only must have f of x, and we have all kind of integration that actually do help us get the solution to such integrand. So therefore the steps into solution now, so what will be it? So it's simply just that now. So it means now if we are facing a problem dy plus p of x y is equal to q of x. The development of those formulas that we saw there, the development there is that we multiply all the terms with this integrating factor. Let me actually use the actual function with the integrating factor. Sorry, this is over x. So integrating factor e raised to p of x, almost wrote to f, raised to p of x dx times dy over dx. So it's a plus a raised to p of x dx p of x here y. So is equal to if q of x, right? As you see, it's have been shown that if this happens, the two terms on the left hand side, they give a product, which is true. In fact, I think it's simply just obvious to anyone that y have its derivative here. I think maybe what may be of an issue is to really agree that this product is a derivative of this exponent. But you can just show, you say if we are having p of x dx, then we use capital letter to actually denote the integral. It therefore means if you come back and you differentiate this capital letter p of x, it means your answer will be small letter p of x. So in any case, therefore, this, it means the derivative of the integral p of x dx, it means the derivative is the small case p of x, which is therefore what you have here. The derivative of all of this top part, the derivative is a small letter p of x that you have here, right? Which is in agreement with the derivative of an exponential function, which we all know that the derivative of e raised to, maybe say z of x, the derivative is a z prime of x times e raised to z of x, right? So realizing that we have a product on the left hand side, so it therefore means we can put the two terms together as a e raised to p of x dx. This is simply in reverse of what we were doing to get to this exponent. So is equal to, therefore, okay, I was supposed to put the exponent here as well. So it's the exponent p of x dx here times q of x. Right. So we want to integrate. Therefore, can borrow this d of x to give the direction, because we might integrate with respect to. So we therefore are left with integral, so e raised to p of x dxy is equal to integration e raised to the exponent times q of x dx plus a c. So this therefore will give us the exponent p of x dx y is equal to the right hand side. Plus the c. So which is something that we appreciate, is exactly what we have on the other side where we started, where we said to get the solution into this problem that you are facing, you just have to get the integrating factor which is this exponent, and you take it and you apply it into this formula. This formula is somewhere in the terms which are not appearing on the screen. So in conclusion here, therefore y is equal to 1 over integrating factor. Again, I'm using the actual function, the exponent. The formula that you have there is having if, is the same thing. So having e raised to p of x here, dx, q of x, dx plus c. So we always talk about this mistake. People, they have a tendency of putting c aside as a standing alone variable. We never do that. You can see this if, this exponential function, must be c over this exponential function. It must be there. Okay, so then this is the solution that you have to get. Right, okay, let's go back. So when you are solving these exercises yourself, you don't have to go through all of this. So here we only were just showing that this is where it comes from. Okay, and erase so it doesn't show. Okay, now let us try to apply this formula. Just 2 exercises will be enough. In fact, even 1 is enough, but I just will do 2. Okay, so there is a first one I have here. I simply just say solve the following ODE, and then it says find a particular solution where possible. Okay, so then they give us the first one, x dy over dx. So the plus 2y is equal to x squared y 2 is equal to 3. So in that statement of saying find a particular solution where possible, for this exercise, it means it will be possible to find a particular solution. The second exercise we have is x plus 2y dx is equal to dy. There is no initial conditions here, so therefore we'll just get the general solution. Okay, so let us try to get the solutions. 1. Let me first rewrite it here. Plus 2y is equal to x squared. So what do we do? Standard form. Therefore, I have to remove this coefficient x, divide all the terms with it. We'll get a 2 over x here, y is equal to x, which gives us a nice standard form that we can solve using using integrating factor method. So the question is, will we be able to use separation of variables in this case? Of course, we cannot be able to, because even if we take the 2 over x, y to the right hand side, we will just have x minus 2 over x, y. This is not equal to this. It's not easy, so we will not be able to have y as a common value in the 2 brackets. So therefore, we just have to find the integrating factor here is equal to the exponent 1 over x dx, which simply is equal to a raised to 2 ln x, which is equal to x squared. We take the integrating factor, you multiply y with it, equal to, you open an integral, integrating factor here if multiplied by q of x times the dx plus the c. me perform integration first. So this line keep disturbing us. Okay, it's gone. Okay, so this therefore have to integrate x cubed dx plus c. So the problem I have here, they give a very simple integrand. So the solution to this integral is simply just x raised to 4 all over 4 plus a c here. Therefore y is equal to x squared all over 4 c all over x squared. Perfect. So this is general solution. So the question comes with some initial conditions. Let me go back and look. Also 2 and a 3. So we have y is equal to 3 when x is equal to 2. So 2 squared will be 4 there. Therefore we have a 1 plus c with a 4 here. Therefore means c is equal to 2 and a 4, c is equal to 8. Therefore in conclusion, y is equal to x squared all over 4, 8 all over x squared. See, there is nothing much. You just solve this problem and we finish like within. It didn't take long. Okay, so let's solve another one. I'll just draw a line like this. I may have to keep extending the line as we go down. Now let us see. Hopefully this problem will only just finish here. The second problem we have here, so it's ax as a plus 2y dx is equal to dy. So we have to put these differentials together into just a derivative. So, and let us try to put it on the left hand side. So the dy over dx, so is equal to, so it's ax plus 2y. So what do we have? We can now solve this using separation of variables. We can only use integrating factor method, and when we do that, we want y to be on the left equal to x. So if y is on the left, then we're able to pull out the p of x function. So the next thing that you just have to do, find the integrating factor minus, put a minus outside, 2 dx here. So this therefore will give us e raised to minus 2x. Minus the other side is only 2x here. So once you have integrating factor, then you multiply your y with e minus 2x, which is your integrating factor. Then what is the q of x? It's q multiplied by e raised to minus 2x dx here plus a c. Then we have to perform this integral. We have to integrate here. So when we try to perform this integration, it seems we're having integration by parts. So let us try to solve this integration by parts first, then we have our solution afterwards. So we can let u is equal to x, which will therefore means du is equal to dx. It therefore means dv is equal to the exponent, which will therefore give us v is equal to e minus 2x all over minus 2. Right? So it therefore means y e minus 2x is equal to uv is therefore minus x over 2, the exponent, minus, according to the by parts, it's a 1 over 2 here. there is a minus also coming with the minus 2, therefore it's a plus here. A minus 2x, therefore dx. Let me say plus a c. Therefore what do we have? So we're having minus x over 2 e minus 2x, that's a plus 1 over 2, times minus 2x all over minus 2 plus a c. We're therefore having a minus x over 2 minus 2x, 1 over 4 e raised to minus 2x plus c. So therefore in conclusion, y is equal to minus x over 2, 1 over 4. The exponents will cancel, plus a c e raised to positive 2x. Positive 2x because it was minus from the bottom. Okay, I think these two exercises are enough. We had that part where we were trying to show where the formulas came from. I think that is what made the recording a bit long, but hopefully it is not so long. Okay, so we will stop here. Then the next thing that we have to do is we'll try to look at some applications. Then we continue afterwards.